was mentioned. In particular, we investigate an encoder-decoder transformer model that is trained on this task. Some of the desired goals of such dialogue responders is to be fluent, relevant to the conversation, and also controllable. In this work, we do not want to achieve these goals by training customized conditional models that exist in the literature. Instead, we want to achieve controllability in a generic encoder-decoder model that is already fine-tuned for the response generation task. So in other words, we aim to achieve controllability by biasing the model and doing this only during testing phase. Existing works in the literature does this kind of controlling using some kind of attribute discriminators. But we want to not use any gradient updates and rather solely rely on the model's robustness to try to extract the controllable patterns. So we propose three broad types of controls: attention biasing, decoder mixing, and context augmentation knobs. And we'll explain each of these knobs one by one. And particularly the scope of this work is to analyze and understand these knobs that we propose, particularly on the generative task of response generation. But the ideas are fairly general and can be extended to other tasks also. Let's start with the attention biasing knob. As the name suggests, the attention biasing knob is applied to the cross-attention block of the decoder of this encoder-decoder transformer model. The way it works is that it takes a normal cross-attention layer and intervenes on this computed attention distribution. So the intervention follows this way. There is a bias vector PT that we design, and this bias vector scales the attention distribution and then renormalizes it. The idea here is that this bias vector can emphasize different parts of the context based on the logical groupings of the context. In respect to our application, these logical groups are basically knowledge and dialogue terms. And we have a subscript T here, which represents the time step of the decoding. So say in this particular figure, the third token in the decoding or in the response is being generated. So this bias vector is for that particular token. The main observation we see by this kind of intervention is that we notice that during inference, when we are applying these interventions, we do not see the model to derail. So it doesn't end up generating gibberish. Instead, it generates logical stuff and controllable stuff. So to explore this further, we design three kinds of bias profiles. The first two profiles are time independent. So irrespective of which token is being sampled or generated for the response, the biasing is going to be same. We have the dialogue bias profile, which emphasizes the dialogue part of the conversation, and the knowledge bias profile, which biases towards the knowledge snippet. And then we have a time varying bias profile, which is called gradual knowledge, which basically as time proceeds in the response, the emphasis is given more and more towards the knowledge. So it switches from priority to dialogue, then towards knowledge. So on a high level, when we apply these kind of biases, the main pattern that we see using these profiles is that when the model is asked to look at the knowledge part, it results in more paraphrasing of the knowledge in the output sample. Whereas when the emphasis is on the dialogue section, we see that the responses are more generic towards the dialogue. So to further evaluate the efficacy of these knobs, we calculate three dimensions, which are desirable factors in knowledge-grounded energy: fluency, relevance, and informativeness. And we include both automatic and human evaluations. So if we look at the numbers, what we see is that given the three biasing variants, there is no statistically significant difference for fluency and relevance between the variants. But when we look at informativeness, the metrics which are calculated with respect to the knowledge now, not with the human response, but with the knowledge, we see a significant increase in precision recall centric metrics. And this increase for informativeness is for the knowledge oriented profiles. So for the knowledge bias and the gradual knowledge bias. And these trends are similar across different splits of the testing set from the topical chat data set that we perform our experiments on. In the paper, we have additional analysis on the effect of magnitude. So how much high or low the biasing value should be, and also where should the biases happen? Should it happen on the upper layers, on the top layers, or the bottom layers, and so on. So we have some of the results in the paper. Coming to the next knob, it's a decoder mixing knob. And the key idea here is decoders basically can be trained to have different skills. Like there can be a decoder for summarization, there can be a decoder for NRG, response generation. And even the pre-trained decoder has some skill that is of reconstruction, because the encoder decoder model is sort of trained like an autoencoder or a denoising autoencoder model. So we try to see if we can combine these skills in some ways, in particular in zero shot. So in addition to having the fine-tuned model, we also have the pre-trained decoder, and we combine this fine-tuned decoder with the pre-trained decoder and see what happens. The way we do it is we send the same input for each layer. We have the pre-trained decoder block and the fine-tuned and the pre-trained. We see it send the same input, and then the output from each of these respective blocks are combined using a convex combination. And then this new output is sent again to both the blocks in the next layer. And the intuition is that the representation is coming from the pre-trained decoder side, given that it has better reconstruction capabilities, would encourage paraphrasing the knowledge in the context and improve the informativeness of the fine-tuned decoder. So when we look at the results of this new knob, which is B, and also the combination of A and B, we see further increase in informativeness scores. So combining attention biasing with decoder mixing gives us even better results without having statistically significant difference between fluency and relevance with respect to the base model. So now we move on to the third knob, which we call the context augmentation knob. And this knob aims to control additional features in the generation, apart from informativeness, such as some kind of syntactic or semantic control. So in the context of response generators, some desirable features are inquisitiveness, which is the tendency to ask questions, having responses that are more positive sentiment or show some confidence behavior or more empathetic in general. And similar to previous knobs, we want this behavior to happen in zero shot. That is, we do not want to train any custom models for each of these type of control that I mentioned. So here we see how we apply the knob C. This whole knob C is applied in 2 stages, which I'll explain now. In stage 1, we curate a set of control phrases. So for example, if the goal is to control inquisitiveness, that is a tendency to ask questions, we'll sample randomly some questions. And these are questions sampled from the training set of the topical chat data set that we use. And then we pass each sentence through the encoder, get its representations. And then motivated from prototypical networks, we take a concept average. So this is basically a candidate or canonical representation of questions, which we call control code. So in the literature, these kind of control codes are normally learned during training. But since we are avoiding training altogether, we have to come up with something which is meaningful to be effective in zero shot. In stage 2, once we have the control code, which is here, we prepend it to an earlier context, which comprises of the knowledge and the dialogue turns. And this overall becomes a new set of contexts now. And once we have this new encoded context, we can now couple it with the earlier knobs, that is particularly the attention biasing knob, where now we can consider this as a logical group and we can increase the bias or decrease as per we need on this particular new group of additional control. We start our experiments by looking particularly at questions, because question asking has been shown to improve engagingness. So question is a good or desirable feature in response generators. So when we see the results, what we first notice is applying only C, which is the context augmentation knob. Although it has some minor improvements, it's not significant. And this kind of aligns to the literature where zero-shot conditioning on controls basically work in very large models like GPT-3, but it hasn't worked in smaller models. And similarly, in our work also, we see the same trend where these are results over the BART base model, which is a fairly small model compared to GPT-3. But the interesting results are in the smaller model, in this BART base model, we are able to achieve zero-shot control by coupling it with the other norms. So C plus A gives better number of questions out of all the whole set of responses that we check. And C plus A plus B performs the best with the highest number of questions. And this doesn't come at the cost of poor relevance or fluency, because those numbers are also still statistically, the difference between them and the base model is still statistically insignificant. So again, in the paper, we have some further analysis on the effective size of the biasing set. So how big should this biasing set be? And also the source of the control phrases. So for this particular example, we sourced it from the in-domain data set, but we also show experiments where we source questions from out-of-domain data sets, and it still works. In the paper, we also look beyond questions and we go into more fine-tuned question types like prop Q, set Q, choice Q. And also, aside from questions, we look into domain acts like feedback, like providing a feedback response, and also to sentiment control in the response. We now come to the last part of the presentation, where we discuss the attention biasing knob again, but this time in the context of self-attention. This is knob D. So it's applied somewhere here, which is the self-attention layer of the decoder. And similar to cross-attention, which was knob A, we also define a bias profile for this attention biasing. And this bias profile is motivated from a n-gram language model where the weight is predominantly on the preceding n tokens, and further tokens are less prioritized or given much lesser weight when computing the next token. But when we do this kind of biasing on the self-attention block, we see that the model has significant effect in the output. In particular, the fluency drops a lot, the perplexity increases, and the model starts generating gibberish. The more we bias, the more it happens. So this brings us to this hypothesis that probably self-attention is highly influential to the fluency of the response. So we hypothesize that it's the workhorse of maintaining the fluency of the decoder. So given this, we see that we notice that if this hypothesis is correct and self-attention is indeed responsible for fluency, what would happen if we mix these self-attentions? And in particular, what would happen if we completely change this self-attention, this fine-tuned self-attention from and replace it with the pre-trained self-attention? So when we do this, this particular row shows that behavior when the self-attention of the response generator fine-tuned on topical chat is fully replaced or it's bypassed by using the pre-trained self-attention, the perplexity degradation is not significant. And in human experiments, we have seen that increase of one perplexity on this data set does not necessarily uh, lead to worse results. They are virtually the same. So this is very interesting because replacing the self-attention did not affect the overall performance that much. And also when we are mixing multiple self-attention blocks, like not just this, but we'll have more self-attention blocks, which are independently fine-tuned self-attention blocks. Even those mixtures are giving good performance, sometimes at par with the original model. So combining multiple self-attention blocks also give good performance, and also this extreme case of replacing it. So this then gives us another idea that, okay, can we fix the self-attention altogether before fine-tuning for a particular task? Because we saw that the pre-trained self-attention was sufficient to maintain the fluency of the fine-tuned task. So can we do that? So this brings us to the last set of experiments where we explore this particular question. In particular, we freeze the decoder except for its cross-attention weights and the shared embedding weights at the outer layer. And we only fine-tune these parameters and keep everything else frozen. So when we do that, we see that there is essentially no difference whether we fix or not fix the self-attention of the decoder. This is very important because we get similar performance with 37% decrease in trainable parameters. So it saves memory and computation from those frozen parameters because we do not need to maintain the gradient subgraphs and the gradient updates for those frozen parameters. And then we can look for even more efficiency by pruning some of the cross-attention blocks altogether. So this time we have 3 variants, wherein each one of them, out of the 12 cross-attention layers, we drop 6 of them and retain the remaining 6. So either we keep the cross-attention at the top 6 layers or the bottom 6 layers or at alternate layers. And notice that for the layers where the cross-attention is dropped, the self-attention directly feeds to the feed-forward network. So the whole cross-attention is bypassed. And it's physically dropped, so the model does not have those parameters anymore. So these are the set of results for that. We see, again, similar kind of results where dropping the cross-attention does not significantly impact the results that much, particularly for this alternate variant where we're dropping every alternate cross-attention block. The results are not that worse. And we believe that this gives us a lot of, it opens a lot of doors in that it opens a lot of avenues for efficient training. Now that we have some conclusive evidence that, okay, self-attention, maybe we can keep it fixed for different applications. So we believe this will be an interesting direction to look at in the future. So with this, we come to the conclusion of this talk. In this work, we presented zero-shot control knobs, and we found that transformers are largely robust to these kind of manipulations that we do using the control knobs during testing phase. And we find that combining these knobs together, the coupling of these knobs, achieve good control in smaller models, which has earlier been seen only in larger models. And we also speculate that the role of the decoder, the self-attention decoder, is towards fluency, is towards maintaining fluency, and find interesting evidence towards this hypothesis. Going forward, we apply these knobs. We would want to apply these knobs in an end-to-end application like NRG, where there will be dialog policies that would basically choose which knob to use at what point. And we can also go beyond NRG and look into more applications with more diverse context, like not just knowledge, but can we have multimodal segments in the context. And the way we have designed our knobs, the extension is fairly trivial. We can also look at better prompt design. For now, we just had random samples of questions. Can we have more complex designs or more effective designs to retrieve or design or learn those control codes. And then the last part of the experiments also open doors for explorations for more efficient training. So these are some of the interesting future directions that we are thinking with this work. And with that, I end this talk. Thank you so much. And if there's any question, please feel free to reach out to me at this email or also to my collaborators. Okay, thank you.
Thank you, Dev. Thank you, Dev. Thanks for the interesting talk. If anyone has questions, please unmute and ask, or otherwise you can also type in your questions in the chat. So I have sort of one question. So when you say that the self-attention blocks are fixed through the pre-trained weights, right? So
Yeah.
I have sort of a general question. So so the attention, the emphasis that it puts on, the current token, the next token, and the further we go away, the emphasis drops, right? In general. But have you observed any scenarios where the decline in the emphasis of the attention values are not that high? For example, like in a human to human dialogue setup, right? We often face this instance where we take a small tangent to another topic, to enrich the current conversation that is going on. This intuitively means that the attention shouldn't decline monotonically, or the least thing to say is that it should have at least a fat tail. So did you observe this in some of your experiments, like the pre-trained self-attention having a fatter tail?
No. So, for example, when we don't induce any kind of bias into the model and allow it to learn itself, we do not always see this kind of behavior, this kind of distribution that I was showing for the biasing. But the particular biasing variant that I showed, where it was diminishing for further tokens, that's kind of inspired. It's kind of an inductive bias inspired from n-gram language models, where the next token you predict is not always on the previous n number of tokens or previous 100 tokens. It's based on previous 3 tokens or previous 4 tokens. So the autoregressive formulation that you have is factorized based on this approximate n tokens in the past. So based on that intuition, we tried to bias and see what happens. See if the model is still able to generate. But what we saw is that the distribution that the model predicts is very different from the human intuition in that sense. So, and the main difference here is it would work if we train with those biases. So if we have a diminishing bias, like the one I showed, and if we train with that, then the model will be forced to learn that. And it will be forced to only look at immediate tokens. But we were not training. We were just introducing this in 0 shot at testing time. And then it doesn't work. But in contrast, these kind of manipulations work when it is on the cross-attention block. So that was the difference.
Oh, so the cross-attention block can introduce, fatter tails. Okay, if
so we tried various kinds of biases in the cross-attention, and that introduced that number one did not derail the model, so it did not make the model generate gibberish, and number two, it behaved controllably. So we were able to show that if you focus on this part of the context, it generates more questions, it generates more responses and stuff like that. But in contrast, in self-attention, the moment we try to interfere, and all of this is in the testing phase. So the moment we interfere, it doesn't work.
Okay. Yeah.
So I think the most interesting
thing here in this work is that everything is applied in zero shot. So we are completely relying on the model's latent knowledge, and trying to understand that instead of introducing our biases and forcing the model to have some constrained learning on that.
Yeah, that
Yeah.
is quite interesting, and yeah, surprising also that the model works fine even in
Yeah.
zero shot case. Yeah, yeah.